Let me continue with the book on page 59, chapter 3, control flow. The control flow statements of a language specify the order in which computations are done. We have already made the most common control flow constructions of C in earlier examples. Here we will complete the set and be more precise about the ones discussed before. 3.1 Statements and blocks. An expression such as x equals 0 or I++ or printf parenthesis becomes a statement when it is followed by a semicolon, as in x equals 0, semicolon, I++, semicolon, printf parenthesis, semicolon. In C, the semicolon is a statement terminator rather than a separator as it is in Argo-like languages. The braces, the open braces and close braces, or the left braces and right braces, are used to group declarations and statements together into a compound statement or block so that they are syntactically equivalent to a single statement. The braces that surround the statements of a function are one obvious example. Braces around multiple statements after an if, else, while, or for on another. Variables can actually be declared in any block. We will talk about this in chapter 4. There's never a semicolon after the right brace that ends a block. 3.2 If-else. The if-else statement is used to make decisions. Formally, the syntax is if expression, else, where the else part is optional. The expression is evaluated if it is true. That is, if the expression has a non-zero value. Statement 1 is done. If it is false, expression is 0, and if there is an else part, statement 2 is executed instead. Since an if simply tests the numeric value of an expression, certain coding shortcuts are possible. The most obvious is writing instead of like this. Sometimes this is natural and clear, and other times it is cryptic, because the else part of an if-else is optional. There is an ambiguity. There is an ambiguity when an else is omitted from a nested if sequence. This is resolved in the usual way. The else is associated with the closest previous else-ness if. For example, in this code, in this snap code, the else goes with the inner if, as we have shown by indentation. As we have shown by indentation, as we have shown by indentation. If that isn't what you want, braces must be used to force the proper association. Like this sentence. The ambiguity is especially pernicious in situations like this sentence. The indentation shows unequivocally the indentation shows unequivocally what you want, but the compiler doesn't get the message and associates the else with the inner if. This kind of bug can be very hard to find. By the way, notice that there is a semicolon after z equals 0 equal a in sentence. This is because grammatically a statement follows the if, and an expression statement like z equal a is always terminated by a semicolon. 3.3 else if the construction. The construction sentence occurs so often that it is worth a brief separate discussion. This sequence of ifs is the most general way of writing a multi-way decision. The expressions are evaluated in order. If any expression is true, the statement associated with it is executed, and this terminates the whole chain. The code for each statement is either a single statement or a group in braces. The last else part handles the none of the above, or devout case where none of the other conditions was satisfied. Sometimes there is no explicit action for the devout. In that case, the trailing else statement can be emptied, or it may be used for error checking to catch an impossible condition. To illustrate a three-way decision, here is a binary search function that decides if a particular value x occurs in the sorted array V. The elements of V must be in increasing order. The function returns the position, a number between 0 and n-1, if lowercase x occurs in lowercase v, and -1 if not. Like this sentence. The fundamental decision is whether a lowercase x is less than, greater than, or equal to the middle element lowercase v bracket mid. At each step, this is a nature for else if. 3.4 Switch. The switch statement is a special multi-way decision maker that tests whether an expression matches one of a number of constant values and branches accordingly. In Chapter 1, we wrote a program to count the occurrences of each digit, white space, and all other characters using a sequence of if, else. Here is the same program with a switch. Like this sentence. So long. The switch evaluates the integer expression in parentheses. In this program, the character C, and compares its value to all the cases. Each case must be labeled by an integer or character constant or constant expression. If a case matches the expression value, execution starts at that case. The case labeled devote is executed if none of the other cases is satisfied. A devote is optional. If it isn't there, and if none of the cases matches, non-action at all takes place. Cases and devote can occur in any order. Cases must all be different. The break statement causes an immediate exit from the switch because cases serve just as labels. After the code for one case is done, execution falls through to the next unless you take explicit action to escape. Break and return are the most common ways to leave a switch. A break statement can also be used to force an immediate exit from while, for and do loops as well, as will be discussed later in this chapter. Falling through cases is a mixed blessing. On the positive side, it allows multiple cases for a single action, as with the blank tab or null in this example. But it also implies that normally each case must end with a break to prevent falling through to the next. But it also implies that normally each case must end with a break to prevent falling through to the next. Falling through from one case to another is not robust. Being prone to disintegration when the program is modified, with the exception of multiple levers. For a single computation, fall-throughs should be used sparingly. Fall-throughs should be used sparingly. As a matter of good form, put a break after the last case. The devote here, even though it is logically unnecessary, someday, when another case gets added at the end, this bit of defensive programming will save you. Exercise 3, middle score 1. Write a function expand parenthesis s, t, which converts characters like newline and tab into visible escape sequences like \n and \t as it copies the strings string s to t is a switch. 3.5 loops, while and for. We've already encountered the while and for loops. In while, the expression is evaluated. If it is non-zero, statement is executed and expression is re-evaluated. This cycle continues until expression becomes zero, at which point execution resumes after statement. The for statement is equivalent like this. Grammatically, the three components of a for are expressions. Most commonly, express 1 and express 3 are assignments A function calls an expression to is a relational expression. Any of these three parts can be emptied, although the semicolons must remain. If express 1 and express 3 is left out, it is simply dropped from the expansion. If the test expression 2 is not present, it is taken as permanently true. So, like this one, like this sentence, is an infinite loop. Presumably to be broken by other means, such as a break or return. Whether to use while or for is largely a matter of taste. For example, in while there's no initialization or reinitialization, so the while seems most natural. The for is clearly superior when there is a simple initialization and reinitialization, since it keeps the loop control statements close together and visible at the top of the loop. This is the most obvious in which is the C idiom for processing the first n elements of an array. The analog of the Fortran or PL/I do loop. The analogy is not perfect, however, since the limits of a for loop can be altered from within the loop, and the controlling visible I retains its value when the loop terminates for any reason, because the components of the for are arbitrary expressions. For loops are not restricted to arithmetic processions. For loops are not restricted to arithmetic progressions. Nonetheless, it is best style to force unrelated computations into a for. It is better reserved for loop control operations. As a larger example, here is another version of A to I for converting a string to its numeric equivalent. This one is more general. It copes with optional leading whitespace and an optional plus or minus sign. Chapter 4 shows A to F, which does the same conversion for floating point numbers. The basic structure of the program reflects the form of the input. Each step does its part and leaves things in a clean state for the next. The whole process terminates on the first character that could not be part of a number. The advantages of keeping loop control centralized are even more obvious when there are several nested loops. The following function is a shield sort for sorting an array of integers. The basic idea of the shield sort is that in earlier stages, far apart elements are compared, rather than adjacent ones. As in simple interchange sorts, this tends to eliminate large amounts of disorder quickly, so later stages have less work to do. The interval between compared elements is gradually decreased to 1, at which point the sort effectively becomes an adjacent interchange method. This code sentence. There are 3 nested loops. The outermost loop controls the gap between compared elements, shrinking it from n/2 by a factor of 2 each pass until it becomes 0. The middle loop compares each pair of elements that is separated by a gap. The innermost loop reverses any that are out of order. This gap is eventually reduced to 1. All elements are eventually ordered correctly. Notice that the generality of the form makes the outer loop fit the same form as the others, even though it is not an arithmetic progression. One final C operator is the comma, like Joe Biden says, which most often finds use in the for statement. A pair of expressions separated by a comma is evaluated left to right, and the type and value of the result are the type and value of the right operand. Thus, in a for statement, it is possible to place multiple expressions in the various parts. For example, to process two indices in parallel. This is illustrated in the function reverse parenthesis s, which reverses the string s in place. Look at this snap. Or snip, S-N-I-P. How does it spell? Never mind. The commas that separate function arguments, variables in declarations, etc. are not comma operators and do not guarantee left-to-right evaluation. Exercise 3, middle score 2. Write a function expand parenthesis S1, comma S2, which expands shorthand notations like a lowercase a to lowercase z in the string S1 into the equivalent complete list ABC, lowercase abc to xyz in S2, allow for letters of either case and digits, and be prepared to handle cases like a middle score, lowercase a, middle score, lowercase b, middle score, lowercase c, and lowercase a, middle score, lowercase z, lowercase 0, no, not 0, 0, middle score 9, and middle score a, middle score z, middle score lowercase a, middle score lowercase z. Fuck, it's complicated. A useful convention is that a leading of trailing is taken literally. 3.6 Loops do while. The while and for loops share the desirable attribute of testing the termination condition at the top rather than at the bottom. As we discussed in Chapter 1, the third loop in C, the do while, tests at the bottom after making each pass through the loop body. The body is always executed at least once. The syntax is do statement while parenthesis expression semicolon. The statement is executed. The statement is executed what then expression is evaluated. If it is true, statement is evaluated again, and so on. If the expression becomes false, the loop terminates. As might be expected, do while is much less used than while and for. Accounting for perhaps 5% of all loops, nonetheless, it is from time to time valuable, as in the following function I to A, which converts a number to a character string, the inverse of A to I. The job is slightly more complicated than might be thought at first, because the easy methods of generating the digits generate them in the wrong order. We have chosen to generate the string backwards, then reverse it. Reverse, inverse, same thing, same word. Synonyms. Okay, here we go. The do while is necessary, or at least convenient, since at least one character must be installed in the array S, regardless of the value of n. We also used braces around the single statement that makes up the body of the do while, even though they are unnecessary. So the hasty reader will not mistake the while part for the beginning of a while loop. Exercise 3.3, middle score 3. In the 2's complement number representation, our version of I to A does not handle the largest negative number. That is, the value of n equal to, what is this? Explain why not. Modify it to print that value correctly, regardless of the machine it runs on. Exercise 3, middle score 4. Write the analogous function I to B, parenthesis n, comma s, which converts the assigned integer n into a binary character representation in S. Write I to H, which converts an integer to hexadecimal representation. Exercise 3, middle score 5. Write a version of I to A which accepts 3 arguments instead of 2. The third argument is a minimum field width. The converted number must be padded with blanks on the left if necessary to make it wide enough. .7 Break. It is sometimes convenient to be able to control loop exercise other than by testing at the loop or bottom. The break statement provides an earlier exit from for, while, and do, just as from switch, a break statement causes the innermost enclosing loop, or parenthesis or switch, to be excited immediately. The following program removes trailing blanks and tabs from the end of each line of input using a break to exit from a loop when the rightmost non-blank non-tab is found. Okay, this sentence. GetLine returns the length of the line. The inner while loop starts at the last character of line. Records that --n decrements n before using the value, and scans backwards looking for the first character that is not a blank tab or new line. The loop is broken when 1 is found, or when n becomes negative, that is when the entire line has been scanned. You should verify that this is correct behavior even when the line contains only white space characters. An alternative to break is to put the testing in the loop itself. This is inferior to the previous version because the test is harder to understand. Tests which require a mixture of ampersand, bar, exclusive, or parentheses should generally be avoided. Three point 8. Continue. The continue statement is related to break, but less often used. It causes the next iteration of the enclosing loop for while do to begin. In the while and do, this means that the test part is executed immediately, and the for control passes to the reinitialization step. Continue applies only to loops, not to switch. A continue inside a switch inside a loop causes the next loop iteration. Here's an example. This fragment processes only positive elements in the array. A negative values are skipped. I'm sorry for the farce. The continuous statement is often used on the part of the loop that follows is complicated, so that reversing a test and indenting another level would nest the program too deeply. Exercise 3, middle score 6. Write a program which copies its input to its output, except that it prints only one instance from each group of adjacent identical lines. This is a simple version of the Unix utility unique. 3.9 Go-tos and labels. C provides infinitely abusable. C provides the infinitely abusable go-to statement and neighbors to branch to. Formally, the go-to is never necessary, and in practice, it is almost always easy to write code without it. We have not used go-to in this book. Nonetheless, we will suggest a few situations where go-tos may find a place. The most common use is to abandon processing in some deeply nested structure, such as breaking out of two loops at once. The break statement cannot be used directly since it leaves only the innermost loop. Thus, this organization is handy if the error handling code is non-trivial, and if errors can occur in several places. A label has the same form as a variable name, and it is followed by a column. It can be attached to any statement in some function as the go-to. As another example, consider the problem of finding the first negative element in a two-dimensional array. Multi-dimensional arrays are discussed in Chapter 5. One possibility is code involving a go-to can always be written without one, though perhaps at the price of some repeated tests or an extra variable. For example, the array search becomes, although we are not dogmatic about the matter, it does seem that go-to statements should be used sparingly, if at all. Chapter 4: Functions and Program Structure. Functions break large computing tasks into smaller ones and enable people to build on what others have done instead of starting over from scratch. Appropriate functions can often hide details of operation from parts of the program that don't need to know about them. Thus clarify the whole and easing the pain of making changes. C has been designed to make functions efficient and easy to use. C programs generally consist of numerous small functions rather than a few big ones. A program may reside on one or more source files in any convenient way. The source files may be compiled separately and loaded together, along with previously compiled functions from libraries. We will not go into that process here, since the details vary according to the local system. Most programmers are familiar with library functions for input and output, getter, putchar, and numerical computations, sin, cos, squared, triangle function, sin, cos, tang, cot. In this chapter, we will show more about writing new functions. 4.1 Basics. To begin, let us design and write a program to print each line of its input that contains a particular pattern or string of characters. This is a special case of the Unix Autodidactism program grab. For example, searching for the pattern in the set of lines. Now is the time for all good men to come to the head of their party. We'll produce the output. Now is the time men to come to the head of their party. What the fuck is that? The basic structure of the job falls neatly into 3 pieces. Although it's certainly possible to put the code for all of these in the main routine. A better way is to use the natural structure to advantage by making each part a separate function. 3 small pieces are easier to deal with than one big one, because irrelevant details can be buried in the functions, and the chance of unwanted interactions minimized, and the pieces may even be useful in their own right. While there's another line is getLine, a function that we wrote in chapter 1 and printed is printf, which someone has already provided for us. This means we need only write a routine which decides if the line contains an occurrence of the pattern. We can solve that problem by stealing a design from pl/i, the function index. parenthesis s comma t returns the position of or index in the string s where the string t begins, or -1 if s doesn't contain t. We use 0 rather than 1 as the starting position in s because C arrays begin at position 0. When we later need more sophisticated pattern matching, we only have to replace index. The rest of the code can remain the same. Given this much design, filling in the details of the program is straightforward. Here is the whole thing, so you can see how the prices fit together. For now, the pattern to be searched for is a literal string in the argument of index, which is not the most general of mechanisms. We will return shortly to a discuss of how to initialize character arrays, and in chapter 5 we'll show how to make the pattern a parameter that is set when the program is run. This is also a new version of getLine. You might find it's instructive to compare it to the one in chapter 1. Code sentence. Okay, so long, so much, so many words. Each function has a form. As suggested, the various parts may be absent. A minimal function is which does nothing. A do-nothing function is sometimes useful as a placeholder during program development. The function name may also be preceded by a type if the function returns something other than an integer value. This is the topic of the next section. A program is just a set of individual function definitions. Communication between the functions is, in this case, by arguments and values returned by functions. It can also be by external variables. The functions can occur in any order on the source file, and the source program can be split into multiple files, so long as no function is split. The return statement is the mechanism for returning a value from the called function to its caller. Any expression can follow return. The calling function is free to ignore the returned value if it wishes. Furthermore, there need be no expression after return. In that case, no value is returned to the caller. Control also returns to the caller with no value when execution falls off the end of the function by reaching the closing right brace. It is not illegal, but probably a sign of trouble. If a function returns a value from one place and no value from another, in any case, the value of a function which does not return 1 is certain to be garbage. The C variable linked checks for such errors. The mechanics of how to compile and load a C program which resides on multiple source files vary from one system to the next. On the Unix system, for example, the cc command mentioned in chapter 1 does the job. Suppose that these three functions are on three files called main.c, getLine.c, and index.c. Then the command compiles the three files, places the resulting relocatable object coding files, main.0, getLine.0, and index.0, and loads them all into an executable file. Call it a.out. If there is an error, say in main.c, that file can be recompiled by itself and the result loaded with the previous object files with the command. The cc command uses a .c versus .0 naming convention to distinguish source files from object files. Exercise 4 middle score 1. Write the function reindex parenthesis s, t, which returns the position of the rightmost occurrence of t in s, or -1 if there is none. 4.2. Functions returning non-integers. So far, none of our programs has contained any declaration of the type of a function. This is because by default a function is implicitly declared by its appearance in an expression or statement, such as sentence like this, if a name which has not been previously declared occurs in an expression and is followed by a left parenthesis, it is declared by context to be a function name. Furthermore, by default, the function is assumed to return an int. Since char promotes to int in expressions, there is no need to declare functions that return char. These assumptions cover the majority of cases, including all of our examples so far. But what happens if a function must return some other type? Many numerical functions like scored, sing, and calls return double. Other specialized functions return other types. To illustrate how to deal with this, let us write and use the function a to f parenthesis s, which converts the string s to its double precision floating point equivalent. A to f is an extension of a to I, which we wrote versions of in chapter 2 and 3. It handles an optional sign and decimal point and the presence or absence of either integer part or fractional part. This is not a high quality input conversion routine that would take more space than we care to use. First, a to f itself must declare the type of value it returns. Since it is not int because float is converted to double in expressions, there is no point to say that a to f returns float. We may as well make use of the extra precision, and thus we declare it to return double. The type name precedes the function name like this. Second, and just as important, the calling routine must state that a to f returns a long int value. The declaration is shown in the following primitive desk calculator, barely adequate for checkbook balancing, which reads one number per line, optionally preceded by a sign, and adds them all up, printing the sum after each input. The declaration double sum a to f parenthesis semicolon says that sum is a double variable and that a to f is a function that returns a double value. As a mnemonic, it suggests that sum and a to f parentheses are both double precision floating point values. And as a to f is explicitly declared in both places, C assumes that it returns an integer, and you will get nonsense answers. If a to f itself and the call to it in main are typed inconsistently in the same source file, it will be detected by the compiler. But if, as is more likely, a to f were compiled separately, the mismatch would not be detected. A to f would return a double, which main would treat as an int, and meaningless answers would result. Linked catches this error. Given a to f, we could in principle write a to I, convert a string to int. In terms of it, notice the structure of the declarations and the return statement. The value of the expression in return parenthesis expression is always converted to the type of the function before the return is taken. Therefore, the value of a to f a double is converted automatically to int when it appears in the return. Since the function a to I returns an int, the conversion of a floating point value to int truncated any fractional part is discussed in chapter 2. Exercise 4.2. Extend a to f so it handles scientific notation of the form 123.45e middle score 6, where a floating point number may be followed by lowercase e or uppercase e, and an optionally signed exponent. Optionally, where a floating point number may be followed by lowercase e or uppercase e and an optionally signed exponent. 4.3. More on function arguments. In chapter 1, we discussed the fact that function arguments are passed by value. That is, they call it function receives a private temporary copy of each argument, not its address. This means that the function cannot affect the original argument in the calling function. Within a function, each argument is in effect a local variable initialized to the value with which the function was called. When an array name appears as an argument to a function, the location of the beginning of the array is passed. Elements are not copied. The function can alter elements of the array by subscripting from this location. The effect is that arrays are passed by reference. In chapter 5, we will discuss the use of pointers to permit functions to affect non-arrays in calling functions. By the way, there's no entirely satisfactory way to write a portable function that accepts a variable number of arguments, because there's no portable way for the called function to determine how many arguments were actually passed to it in a given call. Thus, you can't write a truly portable function that will compute the maximum of an arbitrary number of arguments, as will the max building functions of Fortran and PS-i. It is generally safe to deal with a variable number of arguments if the called function doesn't use an argument which was not actually supplied, and if the types are consistent. Printf, the most common C function with a variable number of arguments, uses information from the first argument to determining how many other arguments are present and what their types are. It fails badly if the caller does not supply enough arguments or if the types are not what the first argument says. It is also non-portable and must be modified for different environments. Alternatively, if the arguments are of known types, it is possible to mark the end of the argument list in some agreed upon way, such as a special argument value, often 0, that stands for the end of the arguments. Okay, it's time to break. Goodbye.